Hey, we're back with Natural Wonders Chapter 9, which is all about plate tectonics. So make sure you have your notes in front of you, and let's get going. The very first two features, 1A and 1B, are both Pangea and Continental drift kind of put together. And you can see the giant landmass that breaks apart. Okay, the giant landmass, its name is Pangea. And that process of the plates drifting apart, moving apart to where they are now, is just simply called Continental drift. So the videos you're going to see are just showing examples of that. The next feature is going to be the lithosphere and the asthenosphere. These are the outer two most layers of Earth. The lithosphere is mainly rocky. It's the crust, how we think of rocks, rigid and cool and brittle. Okay, the lithosphere is where rocks act like rocks. If you go below the lithosphere, you have the asthenosphere. And this layer of Earth acts a little bit different. Because of the heat and the pressure, rocks act more like Laffy Taffy, like a really good piece of Laffy Taffy, not like bad Laffy Taffy, really good Laffy Taffy, that you can bend it without it breaking. And there's some flow that happens in the asthenosphere. After the lithosphere and asthenosphere, there's a quick travel, like you're in an elevator, going up from the center of the planet to the surface. Number 4 is going to be a divergent boundary. And divergent boundaries are where Earth's plates are moving apart. They're diverging, moving away from one another. And this happens because the convection currents come up right below these divergent boundaries. So they bump into the bottom of the crust, they turn sideways, and they move apart. And as those convection currents move apart, the friction they produce with the overlying plate makes the plate move the same direction as the convection current. And so we have divergent boundaries. This is where seafloor spreading takes place. It's where we have those micro eruptions, those little volcanic eruptions that happen every single day all the time. The movement is extremely slow, just being about the rate that your fingernails grow. Next, we're going to get into our convergent boundaries. And we're starting with a convergent boundary that shows an ocean to continent convergent boundary. So we have an ocean crust colliding with a continental plate, okay, land. And what happens is the ocean crust starts to subduct. It goes below the land. And that's just simply composition, okay? Because the ocean is made out of more dense minerals, okay, that more mafic composition group, it's going to be more dense and it's going to subduct or go below the continental crust because it's a lower density. And as it goes into the asthenosphere, into the mantle, it causes melting by releasing water. And then that magma, now in the asthenosphere, is forcing its way up through the continental crust. And that's when we get volcanic mountain ranges, like the Cascades, like Mount Rainier and Mount St. Helens. The next convergent boundary is an ocean-to-ocean convergent boundary. And here, since they're the same type of crust, they're both ocean crust made out of basalt and gabbro, the one that is older is the one that is going to subduct, because the older ocean floor has more time to cool and contract and increase its density, so that one is going to subduct over the younger ocean plate. Very similar situation happens as ocean to continent, where that subducting plate pulls into the mantle water. That causes melting, that makes magma, and now we have magma rising through an ocean plate that produces volcanic islands, like Japan and the Aleutian Islands. The last convergent boundary is continent to continent. And since both of these plates are low density, they're very buoyant, they like to float high in the mantle, when they collide, all they do is jumble together like two chunks of Play-Doh and they end up making these really tall mountains. Big, folded and faulted metamorphic mountain ranges, just like the Himalayas or like the Alps. There's no subduction, so there's no active volcanism. Number 6 is a transformed fault. And transformed faults are the horizontal movement of plates. So they're not going towards each other, they're not moving away from each other, they're just moving past each other like cars on a road, just moving past each other horizontally. The most common place that we have these transformed faults is actually the bottom of the ocean. That divergent boundary that we saw earlier on the ocean floor, it's not just a straight line in the middle of the ocean, it's offset. And every time we have one of those offsets, you can see in the video that that's where transformed faults happen. The very last feature is convection current. In convection current, this is the driving force of plate tectonics. This is the reason why our plates move around Earth in the first place. It's the rising of warm material from the center of the planet towards the outside. When that warm material bumps into the bottom of our tectonic plates, it turns sideways and it moves the same direction. Okay? It forces along our plates to move across the Earth. But as it moves under the plates, it cools off, increasing its density. And when it becomes more dense, it'll sink back down towards the mantle, okay, towards the core. And then it's going to be heated up because it's lower in the mantle and it's heated by the core, and then that process just happens again. Because it's warmed up, it has a lower density, it rises to the bottom of the crust, spreads out, moves the plates, cools off, sinks, and we just have this continuous cycle that pushes around our tectonic plates. All right, if you have any questions, please make sure to ask. Otherwise, study hard for our very last quiz. Thanks.